What are Lagrange points? Lagrange points, named after the Italian-French mathematician Joseph-Louis Lagrange, are unique positions in space where the gravitational forces of two large celestial bodies, such as the Sun and Earth or Earth and the Moon, create a stable and dynamic equilibrium. At these points, the gravitational pull of both celestial bodies precisely balances the centripetal force required for a smaller object, like a satellite or spacecraft, to remain in a fixed relative position with respect to the two larger masses. Lagrange points were discovered by the Italian-French mathematician Joseph-Louis Lagrange in 1772. The 5 Lagrange points are designated as L1, L2, L3, L4, and L5. Lagrange points are important in space exploration and astronomy because they offer stable positions in space where spacecraft and observatories can operate with minimal energy expenditure to maintain their positions relative to celestial bodies. These points have been utilized for a variety of missions, including Earth and solar observation, asteroid tracking, and more. L1, Lagrange point 1. Located on the line connecting the two massive bodies, closer to the smaller body. At this point, the gravitational pull from the smaller body and the larger body balances out, allowing an object to effectively hover in place relative to both bodies. L1 is commonly used for spacecraft, such as the Solar and Heliospheric Observatory (SOHO), to observe the Sun without being eclipsed by Earth. Lagrange point 2, located on the line connecting the two massive bodies but on the side opposite the smaller body. Objects at L2 can maintain a relatively stable position with respect to the larger body and the smaller body. Telescopes like the James Webb Space Telescope (JWST) are planned to be positioned at L2 to observe distant objects without interference from Earth's atmosphere and heat. L3, Lagrange point 3, located on the opposite side of the smaller body, along the same line as L1. It is less stable than L1 and L2 and is rarely used for missions. L3 is mainly of theoretical interest and has not been utilized for any significant space missions. L4, Lagrange point 4, located 60 degrees ahead of the smaller body in its orbit around the larger body. L4 is associated with an equilateral triangle formed by the three bodies. Objects at L4 move in a stable orbit, effectively sharing the smaller body's orbit at a constant angular distance. Some asteroids in our Solar System are found near L4 of Jupiter's orbit. Similar to L4, L5 is also located 60 degrees ahead of the smaller body but in the opposite direction of its orbit around the larger body. It forms another vertex of the equilateral triangle. Objects at L5 also move in a stable orbit. Trojan asteroids are a well-known example, as they share their orbit with larger planets such as Jupiter and Neptune. Stability. Among the 5 Lagrange points, L4 and L5 are stable, while L1, L2, and L3 are unstable. This means that objects placed at L4 and L5 tend to stay in their positions, while those at L1, L2, and L3 require constant adjustments to maintain their relative positions. Orbital dynamics. L4 and L5 form the apexes of equilateral triangles with the two large bodies at their vertices. L1, L2, and L3 lie along the line connecting the two massive bodies, with L1 being closer to the smaller body and L2 farther away. Trojan asteroids. L4 and L5 points are often home to groups of asteroids known as Trojans. These asteroids share orbits with larger celestial bodies, like Jupiter and Mars. They were named after characters from the Trojan War, such as Agamemnon, Achilles, and Hector. Mathematical significance. Lagrange points are a fascinating outcome of the general three-body problem, a mathematical challenge that Joseph-Louis Lagrange successfully addressed in his 1772 paper. They represent a beautiful intersection of celestial mechanics and mathematics. Exploration challenges. While Lagrange points offer unique advantages for space missions, they also pose challenges. Satellites stationed at these points must continuously make adjustments to maintain their positions, and their stability depends on the mass ratio between the two large bodies. Lagrange points are critical for a variety of space missions, including but not limited to astronomy. Space telescopes like the James Webb Space Telescope stationed at L2 offer unparalleled views of distant galaxies and objects in the cosmos. Space weather monitoring. SOHO at L1 helps monitor solar activity and its impact on Earth's climate and technology. Satellite communication. Satellites at L1 and L2 can provide continuous communication coverage for Earth. Scientific research. Studying Trojan asteroids at L4 and L5 can provide insights into the early solar system's formation. In summary, Lagrange points represent fascinating intersections of physics, mathematics, and space exploration. They offer invaluable opportunities for scientific research, satellite deployment, and space missions, making them essential in our quest to understand and navigate the cosmos. Thank you so much for watching my video. As a newbie in the YouTube world, your support means the world to me. If you enjoyed this content, please hit that like button, subscribe to my channel, and don't forget to turn on notifications so you never miss an update. Your feedback and comments are highly appreciated, and I can't wait to share more exciting content with you in the future. Stay tuned for more, and let's grow together on this journey.